The last lecture today. It's about EM waves. Let's put everything we know together. Basically Maxwell's equations, 4 of them. I will give them to you in integral form, and then I think it's late enough in Calc 3 that you should know the differential form of that. We will use that to do the wave equation, and that's the end of it. So here's what we know so far on Maxwell's equation. We know that the integral of E dot dA is equal to the charge enclosed over epsilon naught, right? We know this. Okay? This is Gauss's law. We also know that the integral of B dot dA is what? 0. That's Gauss's law for magnitude. Basically, there are charges, there are electric charges, no magnetic transport. Then we have this one. E dot ds is equal to minus ddt of the magnetic flux. Right? This one is which law? Faraday's law. Faraday's law. And then this one, d dot ds is equal to mu naught times I think it says through. This is whose law? Ampere's law. So there is an issue with this law. That's the final fix that we need to deal with. And then once we fix that, we would have the final form. So there is an additional term here, and then you would have the final form of Maxwell's equation. And by the way, how does matter or charges, how do they respond to electric and magnetic fields once you know them? Well, they will apply a force, and that's called the Lorenz Force Law. And it is F equals to the charge times the electric field, and then the charge times the velocity crossed through the magnetic field, then you can factor the Q, and that's the force. Okay. So all of these we know, right? So the question here is something is missing. So how did Maxwell know that something is missing? So here is a motivation of how he knew that. So suppose what's missing here and why is it missing? So here is what's going on. So suppose you have a current and you have a capacitor here. This is a capacitor. Let's make the capacitor slightly farther apart. And let's say the current is flowing like this. So obviously maybe there is a battery here that's causing the current to charge the capacitor. So the capacitor would have plus charges here, minus charges here, and the current is this. Okay. So first of all, let's say I want to find the magnetic field here. What do I do? Use your right hand rule, and you see that the magnetic field will go like this, right? Okay. Perfect. And so this is Ampere's law. It says B dot ds. Let me do a closed loop. Here's a closed loop. A closed loop. And the loop goes like this. So there is current going through the surface, right? So when I say the surface, what do I mean by the surface? So you have the rim here, that's the loop, and attach the surface to it. It's like a soap bubble, like here. And that soap bubble does not have to be flat. It can bulge a little bit. Okay? As long as it's a surface bounded by this loop, it should apply. So here it applies because the current goes through it, and this is fine. So I come here, I put a compass, I will read the magnetic field. Right? There is a magnetic field. See, the magnetic field doesn't depend on my mathematical surface. If there is a magnetic field, there is a magnetic field. But the law is written in mathematical terms, so we should have it consistent. So now, let's say, instead of my surface being flat, I'm going to choose my surface to bulge a little bit this way. So is there a current passing through this surface? Yes, there is. Yeah, there is current piercing through it. Right? So the surface looks like this now. And this is the loop still, and the current still goes through that surface. So there is current going through. Now, if I choose my surface here, right, the loop, and that's the surface, it's even bigger. Is this fine? Is there current going through it? Yeah, this is fine, because there is current passing through the surface. And so it's still consistent with Ampere's law. Here's the problem. Let's say I choose my surface to be, that's the loop, and here's the surface. Now how much current is going through that? 0. There is no current going through it. So that's an issue. The left side is still true, you got your magnetic field. But the right side, it says the current through is 0. So there is something missing, so that to be consistent, when the current through is 0, there has to be something that makes up for that to tell you, to give you the right equation or the right number for the magnetic field. So what is the missing there? So to fix that, this is a capacitor. And in the capacitor, there is a magnetic field. And the magnetic field, at least in this picture here, points in this direction, right? That's I'm sorry, did I say magnetic field? Yeah. Electric field. I meant to say electric field. So there is an electric field pointing to the right. Now how much is the electric field? Suppose the plate has charge Q and area A, then I know that, let me start with this equation because I want to fix it. So it's called I'm going to pretend I have a current, and current is dq dt. This is the charge, dq dt. So the current will look like this. It's called the displacement current, by the way. Let me call it D. This displacement current is dq dt. Okay? dq dt. Now I'm going to modify this to write it in terms of the electric field. I will multiply by the area and divide by the area. That's legal, right? You can, as long as you multiply and divide by the same number. So I'm going to do this, ddt of the charge times the area, and then I divide by the area. Okay. That's fine, right? Because it's A divided by A is 1. And I'm going to also multiply by epsilon naught and divide by epsilon naught. Like this. Okay. So I get ddt, actually, let me call out the epsilon naught, one of the epsilon naughts. Epsilon naught, and then I have ddt. So let's see if you recognize this. So one of the epsilon naughts is gone. What is the charge over area?
No.
Surface charge density, sigma. And what is sigma over epsilon naught? So Q over A gives you sigma, and then sigma over epsilon naught is what? From Gauss's law way back. It's the electric field between the plates. It's the electric field between the plates. So this here, that's the electric field, E. Epsilon naught has been pulled. So I got the electric field times area. What is electric field times area? It is the electric flux. Yeah. So here you will end up with, once you pull the epsilon naught, you got the electric flux. So the missing part is this. Epsilon naught, I'm sorry, to make it correct dimensionally, I need mu naught times current. So mu naught times epsilon naught times the time derivative of the electric flux. That now fixes Maxwell's equations, and now it's or fixes Ampere's equation or Ampere's law, and now this is good. It's good. Now, of course, it has to be verified experimentally and so on, right? You can't just. This is the theoretical way, and of course, it has been verified. This is from the 1800s, so that's the fix. So now these four constitute Maxwell's equations. Okay, and that's it. So now, if that's okay, I want to just do a couple of problems from the homework, and then move on to the waves, electromagnetic waves. So here is the first problem. Let me make sure I get it right. So this is from homework 14, right? It's a pretty short homework set just to get us familiar. It looks like you have this kind of box. This is a box. Okay. That's the box. The box is 1 centimeter this way, 1 centimeter this way, and 2 centimeters that way. So it's 1 by 1 by 2. So meaning the area of this side is 2, the area of that side is 2, the area of this side is 1, that side is 1, right? 1 by 1, so. And then they give you the following. Suppose there is magnetic field entering from the top. There is magnetic field going into our box, and it is 2 Tesla. There is magnetic field, so there is magnetic field entering from the top, and it's 2 Tesla. There is magnetic field entering from the bottom, and it's 1 Tesla. Let's draw the other one with a different color. There is magnetic field leaving from the side, from this side. There is magnetic field leaving, and it is 3 Tesla. There is magnetic field leaving from that other side. Is that clear? Leaving from this side behind. I'll try to draw it this way. It's also 3 Tesla. And then there is magnetic field entering from the back, from here, or leaving. Yeah, entering. Yeah, entering from the back. And it's 2 Tesla. The question is, the only thing that remains is this space. How much magnetic field is entering or leaving? How much magnetic field? What is the magnitude of the magnetic field, if any? And is it entering or is it leaving? Okay. Is it entering or is it leaving? Now, what do I know? What's a good starting point? Yes?
B dot dA equals 0.
B dot dA is equal to 0. Yes. The flux, the net magnetic flux entering or leaving has to equal to 0. Yeah. So that's right. So let's agree on the following notation. If the flux enters, or if the flux leaves, let's say it's positive, and if it enters, it's negative. Okay. Let's just say that. You can do it the other way. So if the flux leaves, it's what? Positive. If it enters, it's negative. So let's start with the leaving first because it's positive. So you got 3 Tesla leaving out of this space. This one. So what's the flux? Magnetic field times area, right? So the magnetic field is 3. And then what's the area? Let me write it with the same color. So you got 3 times the area. What's the area? Don't worry about the units. It's 2 by 1, right? So 2 by 1. It's centimeters, but everything would be centimeters. The right hand side would be 0, so they would cancel anyway. So that's that. This one is leaving, so it's 3 Tesla times what? 2 by 1 also, right? Let's go to the orange ones. You got 2 Tesla entering, so I'm going to count it as negative. And then what's the area that it goes through? It's also 2 by 1. You got 1 Tesla entering from the bottom, it's negative 1 Tesla. And then the area from the bottom is 2 by 1 also, right? Yep. And then from this end, you got 2 Tesla entering, and what's the area there? So it's negative 2 Tesla, and it's 1 by 1 because it's negative because it's entering. And then the other one, I don't know whether it's positive or negative, so I'm just going to call it B. Who knows what it is? If it's positive, it will come out positive. If it's negative, it will come out negative. And then it is also 1 by 1. And when I add them all, I should get 0, right? In accordance to this. B dot dA has to be 0. So let's add them. So let's see here, you got 3 times 2 is 6, and another 6, so that's 12. 12 minus 4, how much?
8.
8. And then minus 2,
6.
6. And minus another 2,
4.
4. So 4 plus B is equal to 0, right?
B equals.
So you got 4 plus B is equal to 0, and therefore B will be minus 4 Tesla, right? So what does this mean? Well, you got 4 Tesla, enter. 4 Tesla. So that's the answer to that. This is from the homework, I forget, I can tell you which problem it is. Chapter 31, problem 6, right? Chapter 31, problem 6. One more. Before I go on, let me do that one more here. It's problem, or maybe, no. So this one is problem 31.10. So you have a parallel plate capacitor that is 5 centimeters in diameter. So a 5 centimeter diameter parallel plate capacitor. Has a 0.5 millimeter gap. So the distance between the plates is what? 0.5 millimeters, right? That's the distance between the plates. So the voltage is increasing between the plates. The voltage is increasing, meaning basically the capacitor is getting charged. The voltage is increasing at a rate, increasing at a rate dV dt. That's the voltage, right? dV dt. Let's see, 5 times 10 to the 5 volts per second. And the question is, find the displacement current. Find I. Find the displacement current. I'm going to go there. So the solution will be there. I displacement, I'm going to write it here. I displacement is epsilon naught ddt of the electric flux, right? The electric flux. Okay, this one. Epsilon naught. So you got epsilon naught. But the electric flux is the electric field times the area, right? Electric field times area. I don't have the electric field, but I have the voltage. How is the electric field related to voltage in a parallel plate capacitor? I know it has been a while.
E times distance?
V, huh?
E times distance?
E times distance is voltage, yes. So so E is V over D. Yeah, E is V over D. Yeah. So here, epsilon naught. Oh, did I forget the ddt? Is that why? Okay, sorry. So there is, yeah, I forgot the ddt here. Yeah. So let me correct it. Yeah. The same mistake. Please tell me. Don't wait. Okay. So you get epsilon naught and then d dt of, we said the electric field is the voltage over distance, and you got the area here, right? So the distance between the plates is constant, the area of the plates is constant, so pull it out. We'll pull it out. So you got epsilon naught times the area over the distance, and then dv dt. And we have everything. So you got your epsilon naught is 8.85 times 10 to the minus 12 times the area over the distance. Distance is 0.5 millimeters. 0.5 times 10 to the minus 3. The area is pi r squared. The radius is 5 centimeters. I'm sorry, the diameter is 5 centimeters. So the radius is 2.5 centimeters, right? But 2.5 centimeters is times 10 to the minus 2 meters. But you have to square it. You have to do pi r squared. And then times dv dt, which is 500,000. 5 times 10 to the 5th. Tiny number, right? You got 10 to the minus 12, and 10 to the minus 4, and here you got 10 to the 5th. It's going to be tiny.
Minus 6.
So the answer is 1.73 times 10 to the minus 5th amperes, which is 17.3
Minus 6.
micro amperes, right? Because it would be 17.3 times 10 to the minus 6, so micro amperes. Okay. So that's that. Now I want to go to waves. So I'm going to go to the waves. So I'm going to rewrite or write Maxwell's equations over, and then I will give them to you in the differential form, because it's more useful to do the EM waves. And then, yeah, we'll go from there. So here are Maxwell's equations, again, with the fix. So you got E dot dA is equal to Q enclosed over epsilon naught. You got B dot dA is equal to 0. You have E dot ds is equal to minus the magnetic flux dt, and then E dot ds is equal to mu naught I through plus epsilon naught mu naught derivative of the electric flux. Right, I just rewrote those 4 equations over. Okay? I just wrote those 4 equations. So now this is called the integral form of Maxwell's equations. Here is the differential form. I will try to convince you of that, of why I'm writing them this way. You will see that it should be clear. So everybody is familiar with the divergence or curl, right? From Calc 3. Curl and divergence.
Curl.
Yeah.
Gradient.
And so this one, basically, this law can be written this way. It's the divergence of the electric field is equal to the rho, which is the charge density, over epsilon naught. And I will show you how this becomes that. And just give me a minute. For this one, it just says the divergence of the magnetic field is just 0. This one can be written as follows. The curl of E, or the cross product of del the electric field, is equal to minus dB dt, and B is a vector, of course. And then for this one, So you can go back and forth, but for this one, del cross B is equal to mu naught times J. J is the current density, remember? Current per unit of area. Plus epsilon naught mu naught dE. Those are the four equations in the differential form. Now, how does that correspond to this? Well, you have two wonderful theorems from Calc 3, Divergence Theorem and Stokes Theorem. That's how that's possible. So here is how it goes. I'm going to go with the first one, convince you that the first one corresponds to this. And then I will convince you that this one corresponds to that. Similarly, you can do the other thing. So here's how it goes. Let's do this. We're going to integrate over a volume, over some closed volume. Yeah, some closed volume. So that's divergence of C over some closed volume, dV. This is a volume integrated is equal to 1 over epsilon naught times the integral of rho over some closed volume. So now, the right-hand side, when you integrate over a volume, the charge density over a volume, what do you get?
Sigma.
Huh?
Sigma.
I mean, what is the charge density? Charge per unit of volume. So if you integrate charge density over a volume, what do you get?
Charge.
The charge within that volume. It's Qn. It's the charge within that volume. So the right-hand side is just Qn over epsilon naught. So that's already there. So this becomes Qn over epsilon naught. Now how about this? You have a volume. And that volume would be bounded by an area. There is an area that encloses that volume, right? So the divergence theorem says you can change this integral to become this. E dot dA, where the area that over which you're integrating bounds the volume. So that's how this becomes this. Okay. So they do correspond to each other.
So that's the derivative form?
That's the differential form. Yeah. And then I'm going to convince you of this one, and that's it. And then we're going to get to EM waves, okay? You have seen this at some point. If you're in Calc 3, you have seen it, I know, this semester. It's late enough that you have seen it.
Gradient.
And if you took Calc 3, you probably just forget. You have seen it, definitely. Yeah,
So that's for the divergence theorem or Stokes theorem?
divergence.
Okay.
We're going to do Stokes in a second. So here is the one called Stokes, this one. I'm going to take this and integrate over the area. So let's take this one and see how it corresponds to this, right? See how it corresponds. So you got del cross E is equal to minus ddt of B, right? I'm going to integrate both sides with respect to some area. So, where's my flat equal sign? Oh. Okay. And then I have to integrate. So, what is B dot dA?
Zero.
Huh?
Zero.
B dot dA over a closed surface is 0, but this is an open surface, and it will have a boundary.
BDA.
It is the flux, yeah, the magnetic flux, yeah. If it were a closed surface, yeah, it would be 0. B dot dA would be 0. But this is the magnetic flux. So on the right-hand side, you have minus ddt of the magnetic flux. How about this? That's Stokes' theorem. It says if you integrate over an area, you can convert it into a line integral over the line that bounds that area. So again, it's like my soap film or soap bubble thing. If you have a rim, dip it in soap, and take it out. There would be an area. The soap would create an area, and that area is bounded by a loop. And so this can be written as E dot ds over the closed loop. Oh, by the way, this one should be closed, right? So this is the area that encloses the charge. Okay, so that's that. So, anyways, I just wanted to assure you that these correspond to these. And now I want to use it. So here is how we're going to use them to get the wave equation. Remember what the wave equation says.
Y equals cosine.
Yeah, the solution would be some sine or cosine, right? Or some form. The wave equation says the following. How do you recognize it? You take the derivative twice with respect to x, to space, and take the derivative twice with respect to time, and they would be equal to each other with some constant. And that constant would correspond to the velocity squared. And so I would remind you of that in a second. So I'm going to start. So these are the equations. I'm going to take this equation, and there will be an identity that I have. So I'm going to start with this equation here. I drew some space. So I'm going to take the curl of both sides. Take the curl of both sides. So this is Maxwell's equation. So I'm going to, one of them, I'm going to take the curl of both sides. So do this and this. Okay. So there is an identity here, and I will tell you what it is. It's if I don't use it, I forget it myself. So this becomes, this is just an identity from properties of curls. So you got this. Where is my identity? Yeah. Gradient of the divergence of E minus gradient squared of E is equal to minus ddt of the curl of B. Curl of B. Now, here's the thing. For electromagnetic waves, we're in a region. Eventually, if you go back, electric fields and magnetic fields, somebody had to generate them, right? You had some currents or charges. But let's say we're very far away from currents and charges. So there is no current and there is no charge in our region, right? Is it clear? So suppose you're somewhere very far in space, there is no current and there are no charges. There are no currents and no charges. So what do you conclude about the right side here? If there is no charge, what would the charge density be? Zero. So the right-hand side here would be 0. And how about here? What's the right-hand side? If there is no current.
0. 0?
The current density would be 0. So basically, if we go somewhere where there are no charges, this is 0, and no currents, this is 0. And the equations become simpler. Becomes divergence of E equals to 0, divergence of B is always 0. And then the curl of B is just related to the time derivative of the electric field. So I have the curl of B on the right-hand side here, and I'm going to substitute this for it. epsilon naught mu naught, the derivative, time derivative of t. Now, what did I say about the divergence of B, of E in a region where there is no, where there are no charges?
Zero.
Zero. So this is zero, and I have this. So I have, both there is a minus sign, so let's get rid of the minus sign, so you get derivative squared of E is epsilon naught, mu naught, second derivative with respect to time, right? Derivative of derivative. E respect. This is equal to radians squared of E 1 over c squared, second derivative of E respect to t. And I think I mentioned already that what is c? It's the speed of light, because 1 over the square root of epsilon naught mu naught is the speed of light. So this is the wave equation, and it's telling you have some wave traveling at the speed of light. Okay? So that's that. So you have a, yes?
So, sure, so if you are way out in space and there's no charges, what does that do to the derivative of the electric field? Then, like if you go, the curl of V?
Curl of B, yeah, this is zero,
Yeah.
and you get epsilon naught mu naught, derivative with respect to t.
Right, well, what would the derivative be if there's no charges? Wouldn't it just be
It's not gonna be zero.
Okay.
Yeah, so what this would tell us that, so what this is saying is a changing magnetic field will produce an electric field, and a changing electric field will produce a magnetic field.
Okay.
So even if there are no charges, as long as your electric field is changing, it will give you a changing magnetic field, and the changing magnetic field will give you back a changing electric field, and it just keeps going. And so, yeah, one feeds into the other. And yeah, so this is the wave equation. It says basically, this is del squared is like the second derivative with respect to space, with respect to x. In one dimension would be ddx squared. Second derivative with respect to x. And this one is the second derivative with respect to time. Yeah,
Is it supposed to be just E or is it E squared?
just e.
Okay.
Now, you can take the curl, just for the sake of time, you can take the curl of this one, go through the same step, and write the result. It would be so you got an electric field, magnetic field, satisfy the wave equation, and they are traveling in a certain direction. We're going to take a special case where they are traveling in the z direction, and see what happens. So we're going to take a special case, which is the, let's say, a cosine solution to this, because the cosine will be a solution. Because the second derivative of a cosine will give you negative cosine up to some constant, and this one also will give you a negative cosine, second derivative with respect to time.